Hello, everyone. My name is Timur. Thank you very much for listening to my talk about C++20. So I've given quite a few talks at CppCon, but actually, obviously, this year it's different. As you can see, I'm giving my talk from home because of the pandemic. So actually, I have not done this before. This is a new experience for me. So I hope it's going to work out. But actually, I think with C++20 and the whole situation that's going on right now, we actually got really lucky because we had a committee meeting earlier this year in February 2020 in Prague. And by the way, thanks again, Hannah and Avas, for organizing this wonderful event. That was a picture of everyone who was there. I'm somewhere in there as well. So if you want to play Where's Wally, then you can try to find me there. And at that meeting, we actually finalized the technical work for C++20, right? And that was just a few weeks before WHO announced the global pandemic and everyone started to shut down and get canceled. So I'd say that was pretty good timing. And actually, just 2 weeks from today, just 2 weeks ago, C++20, the C++20 draft international standard has passed the international ballot, which means that now it's all approved. It will now just take a couple of weeks before ISO is going to publish the new C++20 standard on their website as the new official standard. So that's just a formality at this point. So C++20 is done. Yay! And yeah, as you can see on the previous picture, the C++ committee actually has grown in size quite significantly from what it was in the 90s. And not only did the committee grow in size, not only did the number of proposals grow in size, but also the number of pages in the C++ standard document grew as well. So here's a graph of the number of pages of all the different published C++ standards. As you can see, while C++98 had 700-something pages, C++20 now has 1,800 pages. And from the number of pages, it's not immediately obvious which of the C++ standard versions were the most significant in terms of impact on the C++ ecosystem. And what I mean by significant is not just adding a bunch of cool features that you might want to use or choose to use, but really fundamentally changing the way we think about C++ code, the way you write C++ code. And the last such release was C++11. So let's remember why. Hang on, my remote. OK, now it works. So let's remember how we had to write code before C++11. So let's suppose you had some kind of vector, and if you want to iterate over that vector before C++11, you actually had to write out the iterator type because we didn't have auto, and those iterator types could be arbitrarily long. If you wanted to sort that vector, you had to actually create a sorted type class. You have to instantiate it. You have to pass it into the sort algorithm because we didn't have lambdas yet. And then actually, whenever you had nested templates, you had to put this like weird white space in between the closing angle brackets because the lexer would always treat two angle brackets in a row as a right shift operator. And then finally, we couldn't even initialize a vector like that, right? Because we didn't have list initialization. So in order to initialize a vector or any other kind of container, here you would have to just manually do pushbacks or do pushbacks in a loop, or we had some horrible boost macros for that. So that was how we used to write C++ code. And since C++11, this looks a lot more familiar and a lot more clean. This is how you write C++ today, because we have auto, we have range-based for, we have lambdas, and the addition of all these features has really significantly changed the way you write C++ code and the way everyone writes C++ code. So looking at this graph again, C++20 didn't add quite as many pages that C++11 did. And in fact, C++17 added a little bit more pages to the standard than C++20 did. So it seems that C++20 wouldn't be more significant than C++17 if you judge by the number of pages. But it turns out that counting the pages is not a very good metric because, first of all, one thing that we had to do from C++17 to C++20 is that we had to change the paper size of the standard document from US letter to A4. Right, so that shaved off several hundred pages. And then more importantly, a lot of the pages that got added in C++17 were like library features that were previously already available in Boost, such as file system, ANI, optional, variant, stuff like that. C++17 added a few core language features. things like structured bindings and class template argument deduction. But I would argue that those are kind of more or less syntactic sugar. Those are things that let you write things a little bit shorter that you could already write before. But C++20 is different because the stuff that C++20 added really changes the language much more fundamentally. It changes the way we think about code. It changes our mental model of what a function is, how to write a template, how to design a library, how to organize, package, and compile a C++ program. So that's why I think C++20 is actually the most significant update of C++ in its entire history. And in this talk, I want to explain why I think that is. So last year at CppCon, I gave this talk about a bunch of small features in C++20. But I think really the reason why C++20 is such a significant update is because of the big features. And mostly because of the big four, as some people call them: coroutines, concepts, ranges, and modules. So let's talk about those. Let's start with coroutines. But before we can talk about coroutines, let's talk about functions. What's a function? So what's our mental model of a function? Basically, a function is a block of code that has a name. You can call it. You can pass it some parameters, which are omitted here. It's not particularly important for the purposes of our talk here. It has some local stack variables. It executes some code, and then it returns a value. OK? So that is kind of our mental model of a function. It didn't really change since the 50s. They used to call them subroutines. They still call them like that in Fortran, I believe. It's pretty much the same thing. It's been around forever. We all know this stuff. So let's look at functions. Let's have a function called f, and then we're going to call it. We're going to get its value, and then we're going to print that value. Okay. So let's say the function returns 0. Okay. So now we are it returns 0. So now we're going to get 0 and print 0, right? So there's this concept of a pure function, which is a function essentially that gives you the same output every time. F obviously is a pure function. So if you call f 3 times and print the result 3 times, you're going to get 0 3 times. Okay, so that's probably not really interesting. But what if you want the function to return different values every time? And let's come up with a really simple example. Let's say instead of 0 0 0, you want to have a sequence like 0 1 2 3. So how do we implement that? And obviously, the kind of simplest way you could possibly do this is you just go in main, you just write a loop, right? And you just increment the loop counter and just print that loop counter. So we can write that. That's very simple. But in practice, you don't really want to write code like that, right? That's not very modular. So what you want to do is you want to kind of separate generating the sequence from printing it, because that's good design. So how do we do that? One thing we could do is we could generate the sequence and put it in a container, like a vector, right? And then the vector, we could initialize it using list initialization, like here. We could fill the vector using a loop. Probably better, we could fill the vector using an algorithm. There's actually in the STL an algorithm called studiota, which generates the sequence. So we could use that, and we're going to talk about algorithms later. But however we do this, we are kind of storing the whole sequence. So the downside of this procedural approach that you have to store this whole sequence in memory before you print it, right? And if you want to print all the numbers from 0 to 1 billion, that's probably not going to be a great approach. So what we want really to make this more optimal is we want to generate the sequence lazily, right? Like we did in the previous slide where we just had the loop. We want to generate each number as we print it, as we need it, right? But still, we want to separate generation of the sequence from printing the sequence. So let's think about how we do that. Let's forget about the container thing, and let's go back to the function. So how do we implement the function f such that it prints 0 1 2? And just think about that for a second. One thing we could do, which we could always do since before C++98, is, well, we could make a counter, which is a static variable, right? And then we can just increment that. And that static variable is going to persist. Next time around we call f, it's going to still have the value it had the last time, so it's going to remember its value, so we're going to get the sequence. But that's not really great, because what we did here is we just introduced global state, right? So that really isn't a good idea. So how do we solve this problem without introducing global state? And then what you kind of end up doing is what we all know, what you're all used to, is you implement a class. You implement a generator class that's going to generate you that sequence, right? So Here I have a class, my generator. I keep the counter as a member variable I. Then we have this call operator here, which is going to return the current value and increment the counter. And then we call that to generate more numbers, right? And this is object-oriented programming. And this is what we've all been doing for decades, and it works. But I would argue that for a task like generating the sequence, it's kind of the wrong approach. It's kind of overkill, right? So imagine what we have to do. We have to generate a new type. We have to decide what member variables we're going to have. We're going to have to decide whether they're private or public. We're going to think about what API does this class have. We're going to think about what class invariance does this class have, right? So there's a lot of stuff to think about, and we think in objects, right? And for a task like generating a sequence of numbers, this is too complicated. This just doesn't feel right. So this is the wrong way to think about this code. And since C++11, there is actually a slightly different way of writing this code. So we can use lambdas. And since C++14, actually, we have this init capture feature. But that is still the same code, right? That's just like a little bit of syntactic sugar on top of the previous slide, essentially, right? So we still have to explicitly create this object state and in the form of a member variable, which is now in the init capture. And it's still the same stuff, right? But it turns out we don't actually have to think in objects at all. So let's go back to functions. Turns out we don't actually need to store explicitly state in member variables because the function already has state, right? So this function already has state in form of just its local member variables, right? Int x equals 0, that's a state, right? So in order to make this all work, we just need to expand our mental model of what a function is just a little bit. And have to imagine that let's just add a little bit to that function. And let's say that the function now can start running. You have this local variable, and then you can yield an intermediate value. And then that's going to return control back to the calling code. But the function is going to still remember its local variables. And then the next time around you call the function, it's going to jump back into where it was at the yield. It's still going to remember all its local variables. And now it just keeps going, okay, until the next yield or until a return at the end. And that's essentially what a coroutine is. And this concept is also not new. It's been around since the 60s. So finally, after 6 decades, we C++ people caught up with the rest of the world, which I think is good. Here's a paper by Melvin Conway describing what a coroutine is in 1963. By the way, that's the same Conway who coined Conway's law, but it's not the same Conway who invented Conway's game of life. But anyway, so now that we have this expanded mental model, let's see if we can solve this problem of a sequence with a coroutine. And if you just kind of keep that mental model in mind, maybe intuitively, how you would want to write this code now that you have this yield thing is something like this, right? So this is not real C++ code, but this is kind of what you would intuitively like to write when you first come across this concept of a coroutine, right? So the counter now is just a local variable, and then we just enter a loop, and in that loop, we're just going to yield the current value and increment the counter, right? And next time around, we call this function, we're going to just go back into the loop, do one more iteration, increment the counter, return the value. And next time around, we call the function, again, increment the counter, return the value. So every time you call f, you're just going to keep incrementing this thing and yielding, and you're going to get the result that you want. And that's super simple, right? Unfortunately, this is C++, so it's not quite as simple. So this code actually won't compile. First of all, instead of the keyword yield, which most other programming languages use, we have a keyword called coyield because of reasons. I'm not going to go into this now. You can ask me afterwards. And the second thing, which is more important, is that the coroutine is not going to return an int. It's going to actually return a generator. And then you have to call that generator to actually get the values. And so you have this like extra step. And that is because C++ is not lying to you. So what actually happens is that the coroutine does not return an int, right? It returns an object, which through the coroutine API will eventually give you an int. And the way to think about this is that the coroutine is essentially like a generator factory. So you call it to get a generator, and then generator will give you the values. And this extra step is there because there's a bunch of choices on how you might want to implement this generator. And so C++ makes that explicit, so it lets you implement the generators. You can make those choices yourself. So it kind of gives you that option. So you have to implement this generator, and then it kind of exposes this whole underlying machinery to you, which is the coroutine API, and that's what you need to use in order to make this work. So this might be a bit confusing. So it's actually not that unintuitive if you just kind of take it apart. So let's take it apart a little bit. So here's the user code. This is our main, right? It's going to call the coroutine. You're going to get a generator, and then we're going to call that to get more values. So G is our generator now. That's a stack variable in main, right? It's going to get allocated on the stack. And what is G? Turns out G contains a bunch of stuff. So the most important thing that you want our int back, right? So that's what you want to print. You want to print 0, 1, 2, 3. So we somehow need to get our int. So it turns out that there's this thing called a promise type. And that's the first thing that's going to be instantiated when you create this generator. And that's essentially the box where the coroutine puts the int and where the user code can get the int out again, right? So think of it as like a std optional of int. It's essentially a reusable box that can hold a single int. And that's essentially our communication channel, right? And everyone needs to have a reference to this promise type. So that's one really important object. And then the other really important thing is this thing called the coroutine handle. And that thing is also going to get instantiated here. And that's standard, that's kind of a magic standard library type. And what it really is a pointer to something that's called a coroutine frame. And what's a coroutine frame? So think about a normal function. The normal function has a thing that's called a stack frame, okay? And the stack frame, that's basically just the internal data structure that your machine needs in order to know how to call this function, right? So for a normal function, the stack frame will contain basically the parameters you pass in. It's going to contain all the local member variables that the function is going to create. Then it's going to contain an address where to jump back to when the function returns, right? And for a function, that stack frame is tied to the lifetime of that stack frame is tied to the stack, right? Because when a function returns, then all of its local variables, they're going to get destroyed. So they're going to get popped off the stack. And that's kind of how a normal function works. So now the difference with the coroutine is that that state can persist. So a coroutine has a lifetime which is independent from that stack. And that's why I need this pointer to it, right? So you can manage the lifetime of that coroutine frame, which is now not anymore tied to the lifetime of the stack. So another way to think about this is if you think about this lambda again, which we wrote here. So we have this init capture here, right? And the init capture is kind of like the coroutine frame for this lambda, because that's the thing that has all the local variables, which is just the I in this case. And so later you can enter that state wherever you want just by calling that lambda. So that's going to be the thing that's going to remember the state of your lambda, which is just the value of I in this case. And so next time you call that lambda, it's going to still know what the value of I is. And the coroutine is really just an extension of that. Like the only difference is that the coroutine has multiple entry points and multiple suspension points, right? But it still only has one coroutine frame that persists all this time, just like it does with this lambda, where it has this like member variable I that persists all the time as long as lambda exists. So you can think of this lambda really as kind of a very simple coroutine, right? So with the restriction that it has to be entered from the top, and it cannot be resumed, it can only return. But you can call it multiple times. And the coroutine is kind of an extension of that in the sense that you can enter it from the middle and you can leave it from the middle. And the other difference is that the coroutine frame, this coroutine frame for the lambda, this I equals 0, we know how big it is, right? So it's an integer, so we know it's going to be 4 bytes because that's the only member that this lambda has. But the coroutine, in general, the compiler doesn't know how big the coroutine frame has to be at compile time. That coroutine frame will then need to go on the heap. It's going to have to be dynamically allocated. So then this is like this dynamically allocated object, and the coroutine handle is kind of this opaque type erased pointer to this object on the heap. So that's the coroutine handle, and that's the coroutine frame. And the generator is really just the user-facing object that kind of groups these two parts together and forwards this kind of coroutine API to the user code so you can use it. So the important thing is, so the coroutine frame is on the heap, but the generator is on the stack, right? And if the generator manages the lifetime of the coroutine frame through this coroutine handle, then when G, the generator, goes out of scope, that's going to destroy the coroutine frame. And that heap memory at that point will be deallocated. Okay, and now the last piece of the puzzle is the actual coroutine. And that's the thing that's going to actually construct the coroutine frame, and that's going to actually run the code that you wrote inside the coroutine. And the interesting thing here is that the coroutine object actually itself is generated by the compiler. So that's why I drew this dashed line in between. And that is because basically that's subject to optimizations, right? So the compiler can optimize this quite a bit. So there's in particular two important optimizations that the compiler is going to do. One is that if you wrote this code in the coroutine, what it's going to do, it's going to take that code and turn it into a state machine, so it can actually manage all this like reentrance behavior more efficiently. So it's going to turn this into something more complicated, but you don't have to worry about that because you still wrote this code in the coroutine that looks really nice. And the other important optimization is that in general, we said the coroutine frame is going to be on the heap because the compiler doesn't know how big it's going to be. But sometimes the compiler can optimize away that heap allocation. And that happens whenever the compiler can see through the lifetime of the coroutine frame, and it can prove that it stops existing by the end of the function. So that's exactly the case here, right? So, and on the left-hand side, we have our main, and then when all that goes out of scope, G is going to stop existing. And if the compiler can prove that no one else has appointed this coroutine handle, so the coroutine handle is never going to escape that scope, that means that basically that's going to be the lifetime of the coroutine. So then the compiler can just like put the coroutine on the stack instead, and everything just collapses, and there's no dynamic memory allocation anymore, and everything is very nice. But because of these optimizations, that's why efficient coroutines need to be a language feature, right? That's what they can't just be a library feature. That's why we need core language support. And that's actually really nice because the code you write on both sides is like really nice and clean. And the code that you get compiled is actually really, really lightweight and very, very efficient. And if you have a compiler that supports that, you can even run it on a bare metal machine that has no threads and no operating systems or nothing. And that's going to be really fast and it's going to be really, really efficient. So that's very nice. And these are really all the bits that you need. There's one slightly annoying thing that this generator type turns out that is not provided in C++20. You don't get that as an implemented type in a standard library. And the promise type is a part of the generator type, really. So you don't get that either. So we're going to fix that in C++23. So there is this proposal by Louis Baker and Quentin Jabot proposing a STID generator, which unfortunately we didn't get in C++20, but we're going to get it in C++23. And that's going to be really awesome. But until then, unfortunately, you have to implement this yourself. Or the much, much better idea is to actually just use a library. There is CppCon, which is a great library written by Louis Baker. So that's what I recommend. Just use that, and then you get a generator that you can use. But when I was looking at coroutines and kind of the specification, the standard, I was kind of trying to figure out how this all works. I got curious, and I really wanted to understand how this works. So I actually went ahead and actually implemented a generator on a promise type, just for this example that I showed you earlier with the sequence of 0, 1, 2, 3. And I just wanted to see what it takes to make this all work, just with standard C++20. And I have to admit, it was surprisingly painful. It took me all day, but I kind of figured it out. So I'm just going to quickly show you what this looks like if you do this yourself. So this is the promise type. And at the top there, you have the current value. That's kind of the box where the int lives, right? That's where we're going to be storing the int. And the coroutine is going to be talking to that object, right? So, and all the other functions down there are really answers to questions that the coroutine is going to ask about how its reentrant behavior is supposed to work exactly whenever it yields and suspends and all of this stuff. And you have a bunch of choices there. And that will basically govern how you're going to implement the body of those functions. So this is really kind of deep into the guts of the coroutine API. But like the really interesting thing here is this yield value function, because that's the coroutine side of the communication channel. So this is where the coroutine is going to put the int into the box. You see it's taking, so you get value, and then it's going to be assigned to current value. So that's where the coroutine is going to store the in that it produced into that box. And then that's a generator. So it has a promise type at the top, and then it has this thing which you already talked about. That's the stud coroutine handle. So that's the pointer to the actual coroutine frame that the compiler generates. And the rest of this class essentially is just a bunch of constructors and basically managing the lifetime of that coroutine handle. So that's really what this is. And this is the promise type that we saw before. And then the other really interesting place, that's the operator paren, that's the call operator. And that's the user side of the communication channel. So that's the operator that takes the int out of the box and yields it to your user code. So that's what you call when you write g paren. And basically, the main message here is, please don't try this at home. Like, I can really can't stress this enough. Like, please just don't do this yourself unless you really, really know what you're doing. There's a lot of subtlety, a lot of choices here. And I managed to write this like very simple one, which I just showed you for this like very simple example. But for something like a more complicated, more realistic use case, I probably wouldn't be able to figure out how to write this correctly. So please just use a library. And if you do that, you get this code. And that's great. This is really nice. It's really clean. It's really efficient. It becomes even more interesting when you have multiple coroutines. So let's say you implement the front end for some programming language, right? So you need to read characters from a file. Then you need to lex those characters to yield tokens. And then you have a parser which is going to consume those tokens and build an abstract syntax tree. So you can either obviously read the whole file, then lex it, and then parse it. And then you're going to have a bunch of classes with members and APIs that do all of this stuff. Or you do it with coroutines. And that's going to be doing it lazily and cooperatively. And that's really nice. So imagine how this works, right? So the parser is just going to parse some tokens. And whenever it needs a new token, it's going to call the lexer. And the lexer is going to be somewhere in the middle of lexing the characters, and it's going to remember that state, and it's going to just like yield the next token, and then the parser can consume that. And if the lexer needs another character or two, then it's going to ask the reader, and the reader is going to yield the next character. And that's all like lazily and cooperatively, and that all really works nicely together. And that's really interesting because it's a completely different way of designing this. And it gets even more interesting if that happens on multiple threads, because then we basically have cooperative multitasking instead of preemptive multitasking. Doing it this way actually avoids another very, very common problem with multi-threaded code, which you might know is callback hell. And I'm sure I've definitely have to deal with this quite a lot. I'm sure many of you need to. If you use objects and you're in this multi-threaded environment where different objects do different tasks, then typically they're going to register callbacks to other objects, and then later when the other objects do something on a different thread, they're going to call back these callbacks, and the callback actually itself is going to be somewhere else in that class. So your logic is kind of scattered across all these different places. It's generally like really hard to debug. It's really painful to work with this. And coroutines make this a lot simpler. So we've already seen that coroutines can yield and return. But in order to make this work, there's just like one more thing that they can do, which is await. And so we have this like third keyword in there, which is co-wait. And how this works essentially is that now we have a coroutine F1 and another coroutine F2. And by the way, as soon as you write any of these three keywords, co-yield, co-wait, co-return, that's how the compiler knows that your function is coroutine, right? So there's no other like syntactic marker for a coroutine. So it's kind of like whether a function is a coroutine is kind of an implementation detail. Whenever you use any of these keywords, that's going to be a coroutine. So that's quite important. So that also, from that follows that you can only co-wait on a coroutine from another coroutine. But now we're in this kind of world where we have these different coroutines cooperating. And so what happens if coroutine F1 co-waits in coroutine F2? So what happens is if you co-wait, so first you're going to suspend, so you're going to return the control back to the calling code. So that's just like with the yield. But the extra trick is then if later F2 yields a value, that's going to actually resume F1, and that's going to jump back into this line of code with the co-wait, and you're going to get the value for you, and then you're going to resume that coroutine, right? So that is really interesting. This is how you can get this cooperative thing work. And this is really, really interesting if F1 and F2 are running on different threads, right? So imagine what that means. And that's actually basically a better mental model of what a coroutine is that co-waits. So the way to think about this, what effectively happens here is that if F1 co-waits on F2, what it's doing, it's registering a callback to F2, and then it's suspending and returning control back to the caller. And then later, if F2 is yielding a value, it's going to effectively call back that callback. And the callback is just the rest of the function body of F1, right? So F1, you have the call wait, and then the rest of that body, that is your callback, right? And that can happen from another thread. And that's actually really, really nice because you get the logic, but you don't have to write it. You don't have to write all these callbacks. So your code ends up being much cleaner, much more compact, and much more coherent because this whole communication channel with the callbacks is essentially just abstracted away, right? The coroutine stuff just handles it. There's only one caveat here, which is quite important. You might have noticed that I wrote async generator here. Because if you have multiple threads going on, you need a fundamentally different promise type, right? So you need to synchronize access to this value u. So you're gonna have a promise type where you're gonna put locks in. You're gonna have to deal with race conditions. So that's gonna be a bit more complicated, and that's actually quite important. So you have to do that in the generator in the promise type, because coroutines, they don't handle that. Coroutines themselves, they don't care about threads at all. They don't care what thread they're running on. And actually, let me repeat that. Coroutines have nothing to do with threads, right? So if your generator type is asynchronous and thread safe, then it all just works. But you kind of have to do that. So yeah, that's, I think, pretty much all the basics that we need to know about coroutines. And this is kind of the mental model behind them, like how to think about them, how to use them to design your code. Okay, let's move on. We have concepts. So let's talk about concepts. But before we can talk about concepts, we need to talk about functions. Here's a function. So that's a function that takes an integer and figures out whether it's a power of 2, right? So I'm doing audio software, so we need that function quite a lot. It's a very clever implementation of it, where you basically do a bunch of bit operations to figure out if exactly one bit is set. So that's really clever, but that only works for integers. Obviously, we want it to be generic, so we want it to work for any integer type. So how do you make that work for any integer type? Well, one way of doing this would be to write out all the 12 overloads. So some people actually do that. That's not a great approach. We have templates, so let's use templates. So we can template it. That's great. We can template it on the type. So we all know this stuff. But what happens if we call this function now with a not integer type? Like, let's say we call it with a double, like a floating point number, just because someone decides to do that. And then we get this really weird error message saying, error invalid operand to binary expression. So imagine you're the user of this, right? And you're like, what does this mean? What did I do wrong? It turns out the compiler tried to instantiate this template with a double, and then it started instantiating, and then it hit this expression with the binary and it turns out binary and doesn't work for floating point numbers. So it's going to issue basically an error saying, well, you can't have a binary and in between two floating point numbers. But that's really basically, in order to figure this out, the user needs to go into the body of that function. You need to find the line of code where the invalid expression was. They need to figure out why this failed. And that's, you shouldn't really be doing that, right? And that's a very simple case. But if you work with real world cases, or if you work with something like Boost, then you probably know that these error messages can get a lot longer and a lot more horrible. And how on earth are you supposed to figure out what you did wrong and what's going on there? So, well, there is a solution to this, right? So we can put a static assert in there saying, well, please assert that T is an integral type. That's much better. Now you get an error message saying, okay, well, double is not an integral type. So that's great. But what do we do if we actually want to make this work for floating point types, right? This is actually useful. Like 0.25 actually is a power of 2, right? So that's useful to know. So, and actually we can implement this function for floating point types. It's actually just going to be a different implementation. But there is actually a very clever way of doing this. So if you want to do this for floating point numbers and you want this to work for negative as well as positive powers of 2, so the way you do this is you have to kind of decompose the floating point number into a mantissa and exponent. And if you've never heard about Std-Frexpl before, then congratulations, now you have, because that's exactly what it does. But if you do that, we get an error message saying redefinition of function template is power of 2. So now we define the same template twice. And that sucks, because that's not what you want, right? The first one is for integers, the second one is for floating point numbers, but you still get this error message. So how do we make this work? And before C++20, really the only way of doing this is Sphina, and the tool we have for that is std-enableif. And let's remember if we let's see if I can remember how to use std-enableif. Okay, so you can write the std-enableif integral type and floating point type. Where do we put this? This is something that I can never remember, right? So you can put this onto the return type of the function, but then you don't really see the actual return type anymore, so that's not great. You can put this into the parameter list, but then you don't really see the parameter list anymore. So I don't like either of these. So my favorite method is actually to put this into the template argument list, because then you can still cleanly see the function signature. So that's, I think, the most readable way of doing this, except it doesn't work. Because it turns out that in C++, defaulted template arguments are not part of the function signature. And then you again have the same function signature twice, and then you again get this error redefinition of function template. Turns out you can work around that because that rule doesn't apply to non-type template parameters. So you can make this an int template parameter. So you can, and that's going to work. That's going to compile. So that's what I've been doing. But just last weekend, actually, I heard from my friend Gaspar Azman that this is actually not good either, because int, people use int as like a legit non-type template parameter. So someone could just like put a value in there, and that's going to break this whole thing. So what you should be doing instead is you should like make it a void pointer non-type template parameter, and you should default it to null pointer. So this is just ridiculous, right? Like, who's supposed to like remember how to figure out how to use this correctly? This is not great. Well, the good news is in C++20, we don't have to do this ever again, because in C++20 we have requires and concepts, and you can just write it like that. So that's really nice. So we have standard library concepts and header concepts like std-integral and std-floating-point. And if you're going to write require std-integral and require std-floating point, and that's just going to work, and this is going to exactly do what we want without any of the ugly stuff. Of course, this is C++, so there's actually 3 different ways of writing this. This is kind of the long form. Then instead of writing a template blah, blah, blah requires, you can actually put the concept name into the template argument list instead of the type name keyword. So you can write template integral t and template floating point t. And then there's an even shorter syntax where you get rid of the template argument list entirely, and you just write it directly into the parameter list, saying concept name auto. And now really the only thing that's still kind of reminding you that this is not a function but a constrained function template is this little auto after the concept name. And that's actually really nice. I think that's a really nice syntax. And we also kind of see why we need different syntaxes for these things, because in the first case, the really short syntax works. In the second case, for the floating point, for the Std-Frexpl stuff, we actually need to be able to name that type, the actual type, t. So that's why we use the slightly longer form where we have template floating point t, so we can name that t. But that's really just kind of scratching the surface of what concepts are. They're like much more than just a more convenient syntax for enable if. You can do much more stuff with concepts. So first of all, you can combine them, right? So if you have this integral concept and floating point concept from the concepts header in the standard library, you can make your own concept of an arithmetic type, which is maybe all the integrals and all the floating point types. So you're just going to say concept arithmetic is integral or floating point. So you can combine them like that. You can also combine them with and. So you can say, well, so for whatever reason, my library is going to accept arithmetic types, but only those with the size not larger than 8 bytes for whatever reason. So you combine that with and actually you can even combine as we can see here, concept names with so concepts with just arbitrary compile time expressions that yield a bool, like this kind of size of thing here. And you can just combine them like that, and that's really nice. And now you have this concept that you need, and you can just write a function, a function template that takes exactly the types that you can accept. So it's constrained exactly on kind of the types that you want here. And if the user then uses that code, if you, for example, pass a double to that function, that's fine. If you pass a long double, that's not going to satisfy this constraint that we defined up there. So that's not going to satisfy this concept my number, but you get a really like meaningful error message. So that's what Clang, for example, gives you. It'd say, well, no matching function because long double doesn't satisfy concept my number because size of is bigger than 8. So I think that's really great. But that's not everything. You can do even more with concepts. We have this thing called requires clauses, where not only can you use combined concepts and combine concepts with Boolean expressions, but this actually lets you encode the exact interface that the type needs to have into a concept and make that a requirement. Like, for example, if you want to implement a hash map and you want to template it on any type that's hashable, so what does it mean, hashable? And then typically it means, well, you can instantiate std hash for it, and if you call that, it's going to give you a hash value, which is an integer. And you can actually just type that out as a requirement and say, my concept of hashable is any type that supports that interface. And that's actually really, really, really nice, because previously, if you wanted to kind of constrain your library interface, like a class or a function like that, you really had two choices, right? So either you would go the polymorphism approach, and you would say, okay, hashable is like a base class, and it has a bunch of like pure virtual functions, and then in order to like have a type, user type that you can use, you need to inherit from that base class and implement all these functions. That's basically what languages like Java do, like object-oriented languages. Or if you want to use templates, the only way to really do this is to just write out in your documentation what the constraints are, like what we have been doing for the last 20, 30, 40 years, like saying, okay, well, if you have a templated on T, then that T needs to have, these and these requirements, and you just write that into the documentation. But now you can write these requirements in code, like in this requires clause, and that is so much nicer, right? This fundamentally changes the way we design our libraries, because we can exactly say what the interface of that type is in code. So earlier, when you were designing a library, like let's imagine you want to write a new library, you would ask yourself, okay, like how do I go about this? Like what classes do I need? Am I going to use like an inheritance like hierarchy and base classes? Am I going to use templates? Like now, the first question you're going to ask yourself is, what concepts do I need to define? And then everything is basically just kind of going to fall out from that. And that is really nice. That changes everything. Once you embrace this idea of like designing libraries using concepts, you never go back. And this lets you write like more flexible libraries, more powerful libraries. And some libraries are just outright impossible to write without concepts. And the best example of that is ranges. Let's talk about ranges a little bit. So that's like the most basic thing. Let's say we have a struct user. So users just have a name and have an age, and then you have a vector of these users. And what you want to do is you just want to sort them by their age. Okay, very simple. So previously you would just use std sort. You would pass it a begin and an end iterator. This is kind of annoying. So a bunch of code bases that I have seen, they actually replace this like begin and end stuff with different overloads of all these like standard algorithms, which just take one argument, which is just your container. So a bunch of libraries have that. Abzile has that. We have it in the code base where I work with at the moment. So that we don't have to write begin and end all the time. And the good news is that ranges are going to give us those overloads in the standard library. So now we just need to pass just the vector, right? So that's great. But it's not just an overload, right? So because it's also constrained with concepts. So if you pass in something that is not a range that can be sorted, you're going to get one of these like really nice error messages. Whereas previously, it would probably explode. And Another feature that ranges have, which is really nice, is this thing called projections. That's like a third argument that algorithms like sort now have, which is really nice. And then the stuff looks like this. So you just pass in a projection onto the member age of this user. And now the age is just an int. So now you don't even need the lambda anymore, because sort already knows how to sort ints if you just pass it stdless, right? That's just the default way of doing this. So now you get rid of this lambda entirely. And that's really cool. So let's look at the declaration of std ranges sort. It looks something like that. And you see, OK, so it takes a range, a comparator, and now it takes a projection as well. And it's a template, but it's also a constraint template, right? So it says that the first template argument has to be a random access range, because we need that for sorting. And then there's also requires saying this requires this thing to be sortable. And what does sortable mean, the concept sortable? So if you look up the definition of sortable, it turns out, well, something is sortable if it's permutable and if there's a strict weak order, which kind of makes sense, right? But it kind of goes all the way down like that. If you look up permutable, it turns out, well, permutable is something that has, at least a forward iterator and is indirectly movable, storable, and swappable. And it's just kind of the whole library, the whole ranges library is really just designed all the way like that. It's really completely built upon concepts. And just imagine for a second how you would implement that if you had to emulate this with std enable if, right? So this would be ridiculous. Nobody, maybe except if you're Eric Niebler, would be able to write that. You wouldn't even try to do that, right? But with concepts, that's just code, right? You can just read it. It makes sense. So let's go back to our vector of users. What else can we do with ranges? So let's make this a const vector, actually. And the reason I'm putting a const there is I want to make this range basically not modifiable. So you cannot modify it in place. And that's really to emulate a range, for example, if you would read the users off the disk, or if you would use the read the users from a network, like one by one, something like that, right? So range that we cannot modify in place. And then, OK, let's do something a little bit more interesting. Let's remove all the users that are under the age of 18, and let's print the age of all the remaining users. And how would you implement this without ranges? All right, so you have a vector of users. So you would then use copyIf with a function or a lambda, basically to filter out the underage users. And then you would use a transform, for example. That's one way of writing this, to print their age. This is kind of not great. This is a lot of code. So a lot of people ask, so OK, why don't we have a transform if in the standard library, right, to make this shorter, to make this one step instead of two? And the answer is, well, if we had transform if, then we also would have to have generative and fill if and all the other combinations, and you will get this permutation, combinational explosion. So that's kind of not the way to go. But how do we combine algorithms? And it turns out, without ranges, really the only way to do this like that is to combine them eagerly in this procedural style, where you do one and then the other and then the other. And that also, unfortunately, means that we need to do the loop over the data twice, right? What ranges allows us to do is we can combine them lazily, like in a functional style. And that's going to look like that, right? So we have these ranges called views, which are just wrapping other ranges. And then you can easily combine them with the pipe operator. And then they're lazy, so the code in the green box is actually not going to evaluate anything. It's not going to loop over the data. It's not going to do anything. It's just going to create this nested structure of ranges. And then down there, when you actually copy them out into an Austrian iterator, which is essentially just another way of saying print this, that's when you're actually going to loop over the data and do all of the stuff. But that's going to be just one loop, right? And the other interesting thing about this is that if you end up chaining ranges like that to achieve your result, you actually end up not writing any loops at all anymore. And that's really nice. So remember when Sean Parent said in his talk in 2013, no row loops, don't write loops. So now with ranges, we really don't have to write loops anymore, right? So because you can just do everything with these chained ranges. But of course, because result is a range and ranges still have begin and end, you can still use them with loops if you want. So you could stick this whole expression, which evaluates to range, in a for loop, in a range-based for loop. You can loop over that, and that has a begin and an end. So that will also just work. And filter and transform are really just two examples. There are many, many more views in C++20. Here's another example. So we have std iota, and then in ranges now we also have ranges version of iota, which is std views iota. And that range just prints the sequence 0, 1, 2, 3, right? And the cool thing about iota is you can print out as many numbers as you want. So it's like, it's lazy, right? You don't have to store them anywhere. You don't have to like put them in a vector. You can just like lazily fetch them one by one on demand. And you don't need any extra memory for that because you never have to store the whole sequence in memory. And that's actually another way of achieving the same thing that we did earlier in coroutines, with coroutines, right? So in fact, that's actually pretty cool because remember when I showed you this paper that we're going to get in C++23 with std generator for coroutines? Std generator itself is actually also going to be a range. So in a weird way, they are just like kind of two sides of the same coin, and I think that's really pretty cool. So yeah, ranges are a big step of evolution for standard algorithms, and I really encourage you to check them out. But we have one more big feature on our list, which is modules. So let's talk about modules. But before we can talk about modules, we have to talk about headers. So headers, we all write headers, we all love headers. That's the world we live in today. Here's the header. So we implemented this generator earlier. Let's put it into a header, right? That's great. And we had this math function earlier, this power of two thing. Let's put that into a math.h header as well. So now we have these two headers. They're great. And maybe let's use them now. Maybe we're doing some stuff with coroutines and some stuff with math. So we need both of those headers. So we hash include math.h and we hash include generator.h. And maybe we have another CPP file where we also need math.h and we also need generator.h, right? So what I mean, this is what we're all doing, but there are so many problems with this, right? So what hash include essentially does is it just copy pastes the code in there, right? It just takes the header and just copy pastes the code into the CPP file. So and that's going to be your translation unit. So whenever you include the same headers into multiple translation units like here, the compiler has to just repeat that over and over again. So it's going to copy paste the code here, parse it, compile it. It's going to copy paste the code there, and this other CPP file, parse it and compile it. And it's going to just keep doing this over and over again. And if you include these two headers in 20 different CPP files, which are 20 different translation units, so the compiler is going to have to parse and compile those headers 20 times. And on the one hand, that's great because that means translation units are independent from each other, so it's really easy to parallelize this. But on the other hand, it's really bad because it's just slow and you're wasting a lot of resources. And it's actually really bad because it actually scales non-linearly with the amount of translation units that you have. So that's really bad. And it's like literally the same headers that you include in the same order. Then you can do some clever stuff like cache it, like Ccache and tools like that. But let's just flip around two of these includes, and all of a sudden it's different code, right? Because the preprocessor is just going to copy paste it in. It's different, right? The order is different. So again, the compiler is going to have to parse and compile this all over again because it's different code now. So that's one problem. Another great thing is you can have cycles between headers, right? So because the preprocessor is just copy pasting stuff, it's not going to prevent you from doing that. So we have to go in and do things like pragma ones or header, include guards. But sometimes you forget to do that, and then you spend 2 hours trying to figure out these weird errors where, something header is included from somewhere else, and you look at this like a long stack of compiler errors, and you're trying to figure out what's going on. And if that were not bad enough, we also have macros. And turns out that macros can basically leak into and out of everything, right? So if you have a macro maybe in other stuff with CPP, just above your header includes, so that macro is going to leak into those headers, right? And it can change anything in there, right? If you define ndebug before you include generator.h, that might change the layout of a class in that header, right? So that's going to be really bad because then you're going to have two different definitions of that class. You're going to have ODR violations. So That's basically like undefined behavior, but it's worse actually because it's undefined behavior on the level of a linker. So you're gonna get some program which is just gonna crash or do something weird. It's definitely not gonna do what you want. You're not gonna get a compiler error. You're not gonna get a warning. You don't know what's going on. It's really fun to debug this. And macros can not only leak into headers, they can also leak out of headers. So for example, if we define a macro in the generated H header, that's going to leak out of the header, and it's going to maybe infect other headers or infect the CPP file and change stuff in there. And that's really bad. And the other really bad thing about headers is that there's really no good encapsulation mechanism, right? So let's say you have this generator, and then maybe you have like some kind of other helper struct, which is an implementation detail, right? And then you don't want users to see this. You don't want users to use this, but you can't really prevent them from doing that. So if if it's a standard library header, if you're a standard library implementer, you can prefix this with double underscore. If you just write a normal library, then people do the namespace detail thing, which is kind of a convention. It doesn't actually prevent anyone from going in and reaching in and doing stuff. So there's really no encapsulation method at all. Modules solve all of this, right? So in the modules world, you would write your generator like this. So that's a module. And now the only things that are visible outside are the things that you export, right? So you export the generator, you don't export the helper. So the helper is essentially going to be a private thing. And also this module is completely self-contained now. You can't have cycles between modules. You can't, macros are not going to leak into the module, and they're going to leak out of the module. So it's completely self-contained. It's going to have, the compiler is only going to have to compile and parse it only once. Actually, what it's going to do is going to, as the first step, it's going to create this thing called a BMI, or binary module interface, which seems a bit confusing because you might think binary module interface, maybe it's some kind of like object file, like .o, like a compiled like binary code. That's not what it is. Binary here just means not text. This is essentially just like an alternative representation of the code so that the compiler can more quickly find all the declarations and definitions in this. So it's going to be some kind of tree structure. And that tree structure is actually going to be specific to the compiler you're using. And it's also going to have things like your current compiler settings, like even the flags that you defined, like what warnings are on and stuff like that. It's going to have your compiler version. So it's really just like an implementation detail of your build system, right? So you should really not distribute this file ever. So that's actually really important. If you give a BMI file to someone else, that other person is going to have a really bad time. So don't do that. But if you have a module, you can now just in your coroutine stuff.cpp, you can just import that module. You can import generator, you can import math. The order doesn't matter anymore. And basically that problem is just solved. So modules are a massive feature. There are many other details and additional levels to this that I didn't cover. There's many other ways to like organize your code and split up your modules into like different subunits and stuff like that. So I don't have time to talk about that now, but the important thing here is that it really fundamentally changes the architecture of your program, right? So it changes how you package up libraries. It changes how we how we compile our code, really. Like it's a huge ecosystem change. So this is just by far the most impactful and significant feature in C++20. So yes, this is these are the big four features. This is kind of what I wanted to say about those in this talk. I see that I have 1 minute left, so I have actually a couple more bonus slides. So we not only have these big features in C++20, but we also have some long-awaited fixes. So one particular thing that every C++ developer stumbles upon at some point in their career, and I'm definitely not an exception, is this thing with removing stuff from vectors. Let's say you have a vector with a bunch of integers, and now the task is to remove all the odd numbers. And I'm sure you've all seen this, right? How do we do this in C++? We have the erase remove idiom. And that's probably the only thing in the standard library that I hate even more than enable if. Because it's horrible. Like everyone just like stumbles upon this. Like everyone, like the first time I wanted to do this, like I did what probably everyone else tries the first time around. Well, you just remove element by element in a loop. And then someone tells you, well, no, that's really slow. That's really inefficient. You have to like do this remove algorithm, except remove is actually not removing anything. It's just moving the stuff you want to remove to the end, except Actually, just this year, I learned that's not even true. It's not removing anything to the end. It's actually moving the stuff that you want to keep to the front, right? So that's what it's actually doing. And when it's done doing that, you need to do this erase, which is going to just basically crop the range to the stuff that the subrange that you want. And this is just horrible, right? So the good news, we never have to do this again, because in C++20, we can just write this. So we have std erase, which just takes the vector, does the job, and that's amazing. So we can forget about erase, remove idiom, and never speak about this again. And I just mentioned this particular one as an example because it's such a common thing. But C++20 has a lot of stuff like this. It just removes a lot of these obstacles. And that makes C++ easier to teach, easier to learn. It's going to make everyday C++ code like this easier to read. And that in itself also significantly changes the way you write code. Thank you very much. That's all I have for today. I believe we don't have time for questions, but just after this talk, I have an AMA session. So make sure you catch me there, and I will be answering all the questions that you have. And yeah, my name is Timur Doumler. Thanks for listening. You can find me on Twitter at Timur_audio. And yeah, enjoy the rest of CppCon. Thank you very much. Are we online again?
Yes, we will be starting the Q&A session now. Now there are a lot of questions, so I'll just start out. So Andrew Castor asks, how can my code control the allocation of the coroutine frame?
Well, I don't think you can really, right? So the compiler is going to create and allocate the actual coroutine, and then in the generator, you have this coroutine handle, so that's where you kind of control the lifetime, but you don't have any control over whether the compiler is going to make a heap allocation or not. So that's kind of something that the compiler might optimize away, but you can't really control that. You can just basically hope that this is going to happen. I'm not sure if that was the question, or if it was just about the allocation of the coroutine frame regardless of whether it's on the heap or on the stack. So that's controlled by, so when you create the generator object, that's typically going to then lead to the creation of the coroutine frame.
Okay, so the next question is, once C++20 is officially published, how long will it be before compilers are ready? I don't understand how long we will need to wait to be able to use C++20 in production code.
Well, a lot of it you can already use. So there's a table actually on CPP reference, which I use all the time. Maybe I can quickly find it and paste the link, which contains a table of like which compiler versions support what C++20 features. If you're like on Clang trunk and GCC trunk and the latest Microsoft Visual Studio, most of the features are already supported. This is actually quite remarkable because within like in the same year where the new standard comes out, like the 3 big compilers already support most of the features. So if you're like an older version of the compiler, if you like, for example, we also ship on like macOS, right? So we have to use Apple Clang. Apple Clang typically like uses like an older fork of Clang, so then we have to wait a bit longer. But yeah, I mean, most of the stuff is available right now. It kind of you just have to be on the latest compiler version. And for some of the things, you kind of need to wait maybe a year. I don't know, ask your compiler vendor, but I think it's not going to be very long. I think within a year, most people will be able to use this. If you can upgrade to the latest compiler, we will be able to like use pretty much all of it, I think.
All right. Next question is, what are the reasons it's named co_yield versus yield?
So there were many discussions about this on the committee. Sometimes it's quite a heated debate, but basically the short version is that because if you make yield a keyword, that's a relatively common variable name, so you're going to break a lot of people's code, right? So yield has a meaning in agriculture, it has a meaning in finance, and has a meaning if you're like making nuclear weapons. And all of these people like use yield as a variable name or like as a class name or something. And we just didn't want to break all these people's code because we just tend to not do that when we release a new C++ standard.
All right, the next question is, what are the performance consequences of coroutines? Does the stored state go on the heap?
So if you refer to the coroutine frame, which is like the internal state of the coroutine, that is in general on the heap. As I said, sometimes that might be optimized away and that end up on the stack. So yeah, you might have an allocation in there. This is actually a concern for me. For example, we're doing like real-time audio. So we have performance constraints there. We can't do like a memory allocation like on a real-time thread. So you kind of have to work around that. You have to like basically call the coroutine and immediately suspend it, and then later you can, and then that's going to allocate the coroutine frame, and then you can call it afterwards, and then that's not going to result in further allocations. So you can kind of work around that. But yeah, the heap allocation has performance implications, but that's only at the beginning, right? When you create the coroutine frame.
All right. Next question. Is it possible to require that a coroutine does not allocate on the heap so that it would fail to compile in that case?
No, that's unfortunately not possible. This is something that a lot of people wanted, and that's part of the reason why it took so long to get coroutines in the standard, because there were all kinds of like additional proposals and competing proposals proposing a mechanism that wouldn't require this heap allocation in general, but then had other drawbacks and other trade-offs, I would say. So there were other designs, but what we actually got in the standard, no, there is no way to basically force a coroutine to never allocate the coroutine frame on the heap.
The next question is, isn't it introducing a state in a similar way as a static variable with respect to coroutines with yield and res?
Yes, so no. So that's an interesting question because that confused me as well for a long time. So no, it's not introducing global state because you have a coroutine which you write once, but if you call the coroutine, you're going to get a generator back, right? And every time you do that, you're going to create like a new coroutine frame, right? So you have a coroutine, you call it, you get a generator back. That's when it allocates the coroutine frame. So you can basically use that generator, but that's an object, right? That's like the generator itself is on the stack. So like if like back in my example, the main function, like when you hit the closing brace, the generator goes out of scope, the coroutine frame gets deallocated. And if you call the coroutine from somewhere else, you're going to get a new generator. So that's going to allocate a new coroutine frame. So that's really so this object that you get back from the coroutine, that's an object. So that's not global state. That's like that instance of that controls the lifetime, right? So it's very much per instance and not global state. That's actually really important. That confused me as well for a long time.
Okay, and the next question is, can coroutines be used in const PR code? I'm not sure if I read that right.
Const expert. That would be really cool, but no. How would this work? Basically, no. As far as I know, that's not possible. But I'm just trying to figure out in my brain whether that would make sense. That's an interesting question.
Should we move on to the next one?
Yeah. So basically, the answer is no, as far as I know.
Okay. So the next one is, how can I know if a function is a coroutine if I only have its declaration?
You can't. Well, like if it returns a std generator or something like that, then it's probably coroutine. But the only way to know for sure is to look into the implementation and see if it uses one of the 3 keywords.
Okay, the next question is, when should you use coroutines versus ranges?
That's an interesting question. I would say if you have a problem that you can solve by chaining like the algorithms that are available in the ranges library, then do that. And if you have something more kind of specific, then then use coroutines. I mean, they're quite different features, right? So the example that I had with the sequence, like 0, 1, 2, 3, that's like a particularly simple one where you can solve it one way or another, and they're like weirdly equivalent. But if you get into more complicated examples, then turns out that they're actually they cover quite different use cases when it comes to more complicated stuff.
Okay. What happens when calling operator after the coroutine has executed co_return?
That's a good question. I don't know that off the top of my head. I would expect that it would probably call to terminate or something like that, or just crash on its undefined behavior. Like I would say it's probably one of the two. Maybe it's just undefined behavior, but I don't know. I would have to look that up. I think it's pretty easy to find that. So thanks. Yeah, I don't know.
Okay. Next question is, what are other use cases for coroutines besides generators?
Well, so one thing that we talked about is this kind of cooperative way of basically combining coroutines together, right? If you have several tasks that are going on, maybe either in multiple threads or even on the same thread, and then kind of they depend on each other's results, and you want to basically lazily use the result of one thing in another thing that you're doing, then that's like a really nice use case for coroutines. It's kind of cooperative multitasking kind of stuff. I think that's kind of the most typical use case, I would say. But there's probably many others. Like this is a new feature, and I don't have terrible amount of experience with them because they're really new. We don't actually use them in production code yet, where I currently work, because like Apple Clang, I think Apple Clang already supports it, but so we're still on CPS 17. So basically we don't use them yet. So there's probably quite a lot other like really interesting use cases that I'm not aware of. I think now that's in the standard, we're going to start using it. We're going to discover many interesting use cases, I would say. So I'm really looking forward to that happening.
All right, the next question is, you mentioned concepts would be an efficient alternative to inheritance, but can concepts in the STD library be safely used in safety critical real-time systems? Are there any known limitations?
Okay, so I didn't say it quite like that. Let me maybe correct that, or maybe I didn't say it very clearly. I apologize for that. So what I meant is, so the alternatives either use inheritance, so like dynamic polymorphism, or you use like templates, which is essentially like static polymorphism, right? So you either use templates or dynamic inheritance, and that's kind of the choice that you have. And once you decide that you're going to go with templates, then concepts give you a very convenient and powerful syntax for constraining those templates and making the interface of those templates, templated classes and functions, more clear, better, more usable. So it's not really an alternative to inheritance. It's like a way to design templated code in new ways, once you already decided you're not going to use inheritance. And the other part of the question, can concepts be safely? Well, concepts are a compile time thing, right? So I don't think that has any implications for real-time systems. So it's very much a compile time thing, right? So either you're trying to instantiate a template, and either your type or your template parameters either satisfy the constraints or they don't, and that's kind of the main feature here. But that's just a purely compile time thing. So the answer is it doesn't matter. It's a good thing for I would use it in real-time code, definitely.
Okay, and this might be the last one we have time for. How do templates interact with modules? As it is now, a template needs to be instantiated in each compilation unit. Can the instantiations/compilations be reused between modules?
So there's, okay, so it's not quite as trivial. I would probably refer you either to someone who can explain the stuff really well, which is probably not me, or we can maybe I can maybe try to talk about this later. It's not a question I can answer easily right now.
Okay, actually we have time for one more. This next one is, can you dive more into modules?
Well, okay, so that's a good answer to that question. There is a talk by Bryce Elsten-Lelbach called Modules Are Here, I think it's called, which is a 90-minute talk just about modules. So he's talking about all of the stuff that I didn't have time to talk about. So just watch that talk. It's a great talk. It basically covers all the features that you need to know. So I recommend you do that. And I can, if you want me to talk more about modules, you can find me later. We can chat about that. There's definitely more that I can talk about here, but not sure if we have time about that.
I think we're out of time now,
okay.
But you can save the Q&A and you can review them later.
All right. So thank you again very much for listening to me for so long, and thank you very much for your questions. Interesting, challenging questions. I have to admit, I don't know everything about how exactly all of these features work, because it's a lot of stuff and it's pretty new. So it's exciting times. Thank you again.